I'm going to talk about machine learning for excited states. And compared to the other talks, my talk will be more on the chemistry side and more on the application side. And I want to start by asking what would happen if there was no light. And I think we can all come up with at least one thing that would not exist without light excitation. Basically, if we look around, the sun is everywhere. Think of photosynthesis, human vision with the eye, or phototherapy. But there are also some negative side effects of light-induced reactions, such as skin cancer, bleaching, or blindness. And if you want to understand why these reactions take place in the way they do, we need to take a look at the chromophores, which can absorb light and give rise to the photochemistry that we are interested in. So there are several ways to study photochemical reactions. And we used excited state molecular dynamics. And a very efficient approach is to do surface hopping dynamics. So surface hopping is a mixed quantum classical method where the molecule moves classically on potentials that are computed with quantum chemistry. Now, this is what you all know from ground state molecular dynamics. But when light enters, there are more potentials that become accessible. So the molecule can access a higher electronic state, and then what we need to do is we need to follow the motion of the molecule on excited state potential. And what you have also seen here is that there can be transitions between the different states. And these transitions are called hops in surface hopping, and they are determined stochastically, and they are based on the couplings between the potentials. So which means that we do not only have to get the energies, we also have to compute couplings if we want to use excited state dynamics. We want to be as exact as possible and want to approximate a wave backend, and therefore we need to sample many different conformations of a molecule, excite all of them, and then simulate their dynamics. And in this way, we get access to the different reaction channels and branching ratios. Now, if you think of dynamics in another perspective, then at every time step, we need to do a quantum chemical calculation. And this means that we sample the conformational regions on the potential energy surfaces over and over again, and this is very wasteful. So I guess I don't have to introduce why we need machine learning, but for excited states dynamics, it's even more dramatic than for ground state dynamics. So if we want to simulate, for instance, the photodynamics of tyrosine, an amino acid, with a multi-reference method, then the simulation of 1 picosecond would take about 10 years. And remember, we need to do this trajectory, these calculations about 1,000 times. And I always ask how many tons of CO2 such a simulation would produce. Any guesses? So this would produce about 840 tons of CO2, which would be equal to the amount of CO2 emission of 70 European citizens. So this is quite dramatic. Of course, we can use also single reference method for a certain conformational region, and then we would still take about 10 months for computation, and it would still produce about 100 tons of CO2. So this is not really sustainable. And therefore, we wanted to replace quantum chemistry and use machine learning instead. And with machine learning, we could get to the accuracy of the reference method, but much faster simulations. So what we wanted to do is we wanted to approximate these potential energy surfaces and couplings to do dynamics. To put this talk in to a bit more context, where can machine learning help for excited state simulation? So for instance, we could use machine learning to get an active space or to show us which density functional we need. And in most talks today, we have heard about machine learning for fitting the primary output of quantum chemistry, which would be basically the wave function or the density. But this is extremely challenging for excited states. And what actually most people do is they focus on secondary outputs. And I will also focus on learning secondary outputs during this talk. So what are these secondary outputs? This would be for excited states, as in ground state energies and forces. And then we need the couplings. So if we want to simulate photochemical processes, then things are much more complicated than just in ground state, because we have our ground state potential here, which would be in blue a singlet state, and then a molecule can absorb light and get excited. Now, if you follow this trajectory here, then you can see that there is an avoided crossing. And this is a critical point on the potential energy surface. And it is also called conical intersection. And you can see that there is a cusp between these potentials. And this region is extremely important to model correctly, but it's very difficult because in machine learning we cannot really get these cusps correctly. Yes, so if you also want to include intersystem crossing and triplet states, then you can see here that this blue line and the red line, singlet and triplet states, they are allowed to cross. So this is also called the adiabatic basis, where the states of same spin multiplicity are not allowed to cross, but states of different multiplicity are allowed to cross. Yes, and if you want to simulate transitions between states of same spin multiplicity, then we need nonadiabatic couplings, and different spin multiplicity spin-orbit couplings. So these are the things that we need to learn. And when we started this work, there was almost nothing known about machine learning for excited states and whether we can actually use it. So we started with a proof of principle. As a proof of concept, we have chosen the methylene ammonium cation. And we've chosen this molecule because it shows ultra-fast population transfer after excitation to the second excited state. So these are the results that we get when we do quantum chemistry. And when we use quantum chemistry for surface hopping, these are the population averages of about 100 trajectories. And in the beginning, the population is in the second state. And there were ultra-fast transitions to the first excited state and back to the ground state. And because this is so fast, we thought it was a good and still challenging example, because if we want to model these transitions correctly, then we need to get the couplings very accurate. For our first study, we stick with the most simplest approach possible. We used multi-layer feed-forward neural networks. And as a descriptor for the molecule, we used the inverse distance matrix. So this was OK, because we just stick to this one molecule, and we didn't change the ordering of the atoms. So the first thing that we had to do was to generate a training set. And we used the multi-reference method, MRCRSD. And we also checked whether we need one machine learning model for one potential, or whether we should describe all potentials in one model. And we found out that describing all potentials in one model is more accurate. We described 3 singlet states and the energies and forces in one neural network and the couplings in another one. So when we started with computing this training set, we had a few goals that it should have. It should have as few data points as possible, because quantum chemistry is expensive, and for larger systems, we cannot compute as many data points. And this training set should still sample the complete space relevance for the dynamics. And this is a problem because we don't know in advance where we will go. So probably if we do just random sampling, we will have a non-comprehensive training set. And if we use it for dynamics, the molecule will just explode. And to overcome this problem, we have adapted the adaptive sampling scheme that was developed by Jörg Behler. And we did it for excited states. And this scheme starts with some initial data that you can get from random sampling or different scans along reaction coordinates. And what we then did was we trained at least 2 machine learning models. And we used both of them in molecular dynamics simulations. And at every time step, we compared the machine learning predictions to each other for energies gradients and couplings. And whenever we left the region that was sampled comprehensively, the machine learning models started to diverge from each other. So we could detect this data point. And we did a reference quantum chemistry calculation, and then we added this data point to the training set. And we thought, yes, in this way, we can get a nice training set for dynamics. But unfortunately, this didn't work as expected. And this is because of the arbitrary phase of the wave function, which plays a role in excited states. I guess that most of you are familiar with the fact that the wave function is not uniquely defined, and it carries an arbitrary phase. And this can be similar to the arbitrary sign, And I want to show this to you with molecular orbitals. So as you probably know, you can either have blue or red orbitals. And we can see this as a sign of +1 or -1. So if we want to compute the energy, then the wave function of the same state enters, which means we have, in both cases, always the same color. So the sign will never change. But if we look at coupling values between 2 states, the wave function of 2 different states enters. And we cannot guarantee that the colors are always the same. which means that once we could have a positive coupling value and once a negative. And if we have the same calculation and give it to machine learning, then it doesn't know what to do. So yes, if we do one calculation, we get an orbital, we get another orbital for the other state, and we get our coupling value. And if we do this along a trajectory, then the sign of the coupling value arbitrarily changes. And this was problematic. So what we did was we developed a phase correction algorithm where we defined one reference geometry, and we then computed the wave function overlap and searched for the right phase, if there was a phase transition or not. So we corrected every data point in the training set. And with this, we got smooth coupling values that we could actually learn. So we needed to correct these data points. Then we could add them to the training set. Yes?
So those two things like conical intersection, the phase changes sort of suddenly, and then often it's not easy to follow orbital along that path. So here I'm assuming you're just starting from the previous calculation, making sure the orbital has maximum overlap. But if the two orbitals sort of mix together, does that such things, do they cause issues?
So when we considered when the character of the orbitals changed.
Yeah. So discontinuously it can change.
Yes. So that was one of the problems. And also what is very problematic is that if you have your reference point and then a point that is far away, you need to do interpolations. And this in regions of conical intersections, they need to be very small so that we can really follow the correct sign. So this is definitely a problem. So we then did many dynamic simulations and sampled lots of data points. And then we could train our machine learning models. And we wanted to know, first of all, if it works. So we needed first to reproduce the excited state dynamics. And here you can see the results of the populations curves computed with machine learning and quantum chemistry. And you can see the continuous lines are the machine learning populations, and they match quite well. So we were quite happy with these results and thought it worked. So because machine learning is much more efficient, we also could compute many thousands of trajectories and get better statistics. And we smoothened the population curves. And this is important if we want to sample, for instance, rare reaction events. And finally, we wanted to see whether we can go beyond the timescales that are feasible with quantum chemistry. So we simulated the first nanosecond simulation for excited states. You can see that the population is transferred to the ground state as expected. But we could achieve this in about 2 months. Today, we would be faster. But with quantum chemistry, it would have taken us about 19 years, and I'm very happy I didn't have to do this during my PhD. So we were quite happy with this setup, and we then wanted to make it more applicable also to other people, not only the developers. So what we did was we combined the nonadiabatic dynamics program SHARC that was developed in the research group of Letizia Gonzalez. And we wanted to combine it with the deep neural network SCHNET developed in Klaus Robert Müller's research group. And together with Michael, we made SCHNARC. So if you're interested, it's freely available on GitHub. And with this approach, we tried to improve on our previous approach. So first of all, Jan has already explained to you, we used the SCHNET descriptor compared to the inverse distance matrix. So SCHNET is a deep continuous filter convolutional layer network. And the nice thing is that it learns the molecular representation based on interatomic distances and atomic charges. So it's a message passing network where we have one block where we generate our descriptor, and then this descriptor goes into the next block to predict the energies. Yes, and the nice thing about it is that compared to just a molecule-wise descriptor, where like the inverse distance matrix, where we can only sample one molecule, we now describe the molecule atom-wise. So we model the atoms in their atomic and chemical structural environment. So if we want to train, for instance, on energies, we get atomic contributions for the energy, and then we sum them up. And this works for molecules of any size and atom type. Now, another limitation that I already mentioned is the phase correction, because it's very tedious and it doesn't always work. So as I mentioned, we compute the wave function overlap between two geometries for every state. Now this is an arbitrary reaction coordinate of a dissociation in tyrosine. In blue we have singlet states and red triplets. Now if you look at 2 angstrom distance here, the first singlet state, if we want to track this back to the reference geometry, then we might end up needing to track to the 50 for 100 state, and this is simply not feasible. So we wanted to overcome this problem and develop the phase-free training algorithm. And as I already mentioned, we don't know whether we have blue orbitals or whether we have red and blue orbitals. And the machine learning model also doesn't know. So what we did was we computed the error twice. So once we assumed that the phase is okay, and once we assumed that the phase changed. So we had a positive error and a negative error. And we give both errors to the machine learning model. And we then use the minimum function as a loss function. So this minimum function that we used as a loss function looks like this. So it is basically the minimum of a vector. And this vector contains the error between machine learning predictions and quantum chemistry reference data point that is multiplied with the phase of state I and phase of state J. So this vector has as many errors as possible phase combinations for every state, and the number of phase combinations are 2 to the power of number of states minus 1. And for a few states, this works very well, but the more states we get, the more expensive this approach becomes. So we validated this for the methylene-ammonium cation. So you can see here the population curves with a normal machine learning model and phase-corrected data. Then you can see if we train on non-phase-corrected data, then the nonadiabatic couplings are not that good anymore. And if we use the phase-free training algorithm and train on raw training data, then you can see that the population curves match much better again, and in the end, we have similar populations. And finally, there is another problem that we wanted to improve, and these are the nonadiabatic couplings. So the first studies always trained nonadiabatic couplings as single values, but they are vectorial properties, and they need to rotate with the molecule. So everyone ignored this in the beginning, and we tried to improve it. But what is also another problem is that the nonadiabatic coupling is inverse proportional to the energy gap, which means if we have here 2 potentials and they form an avoided crossings or the conical intersection, then the coupling values are singular. And what we did during a collaboration with Anatole von Lilienfeld, we trained interstate coupling. So we multiplied the nonadiabatic coupling values with the energy gap. And in this way, we could smoothen the coupling values. So what we predicted then was basically a latent value, a latent property, and we derived it. And in this way, we got the rotational covariance correctly. And then we multiplied it with 1 divided by the energy gap. And the energy gap was also obtained from machine learning. But this was another problem because with this approach, we needed very accurate energy potentials. And we cannot really get the conical intersection very accurate. So we also couldn't get the couplings very accurate. They were improved, but not that much. So we also tried to use another approach, and this was based on only energies and forces. And we wanted to approximate nonadiabatic couplings. And we used back uncouplings for this. So this is based on the squared energy difference and the second derivative. And this approach actually existed for like 40 years or so, but it was never used because getting the second derivative with quantum chemistry is super expensive. But we revisited it because with machine learning, you can get second-order derivatives much quicker. So we used this equation here where we have the second derivative of the squared energy difference and the gradient difference vectors. And so we have a symmetric dyad, and if we do singular value decomposition, then we get the eigenvectors, and the eigenvector that corresponds to the largest eigenvalue could be used to approximate nonadiabatic couplings. So we could actually do surface hopping with only energies and forces. And you can see here the population curves that we obtained if we use this approximation, and it looked actually quite nice. So in the end, we had a setup that worked quite well, and we wanted to apply it now to a more complex system. And the system that we wanted to study was the amino acid tyrosine. So why should we be interested in tyrosine? Tyrosine is one of the amino acids that can absorb light, in the UV visible range, and thus this gives rise to the multifaceted photochemistry of proteins and peptides. So its proton-coupled electron transfer plays a role in photosynthesis. Photodamage can lead to skin alteration and cancer, to blindness or to drug alteration. But what kept our interest was that there was experimental evidence for photodissociation after light excitation. And what is more is that the experiments suggested a size dependency in the dynamics, which means that the dynamics get faster the larger the system. And in phenol, we only see mainly hydrogen dissociation. But in larger chromophores, we see carbon-carbon bond cleavage or decarboxylation or other things. And because the computation of the excited states of tyrosine is extremely expensive, many theoretical studies only focus on the smaller chromophores. And we wanted to know whether the mechanisms in excited tyrosine are similar or different to those of smaller chromophores. So this was our motivation. And we wanted to complement experiments. So we needed to find out how many states we need to calculate in order to do so. So the experiments, the pump probe experiments were used laser pulse excitation at 200 nanometers. And in gray, you can see here the excitation window. And you can see that this energy range is where the fourth excited singlet state is. So we knew we needed 5 singlet states. And we also found some literature where they talked about phosphorescence. So we could not just exclude the triplet states, and we also needed as many triplet states as that are within this energy range. And we found that 8 triplet states were important. So we had 13 adiabatic states, and we needed to also learn now coupling, as spin orbit couplings and nonadiabatic couplings. The next thing that we did was we selected the reference method. Now, if you want to simulate the breaking and the formation of bonds, we need multi-reference methods. So we tested different methods, and like Cassasieff or Caspididou, and you can see here the potential energies along this dissociative coordinate. And in blue, we have singlets and red triplets. And you can see that the potentials are far from being smooth. So they have some random jumps in energy. And this was extremely problematic to fit because also the density of the states was very high. So this didn't really work. So we looked at single reference methods like ADC2 or TDDFT, and we found that we had smooth potentials. But the problem with these methods is that it's very difficult to model bond breaking and formation. So at large interatomic distances, the singlets and the triplets should be degenerate, because if the hydrogen and the oxygen is here and we have spin up, spin down, and the hydrogen moves away, then it should not matter if the spin is up or down here, because they should not feel each other. So the states should be degenerate, but they are not. So this is not physically correct. So what we were basically left with was a machine learning setup that finally worked, but we couldn't use it for any system rather than small models. And we didn't know where to get the potential. And no matter which method we have tested, we couldn't sample the whole phase space that was relevant for the dynamics. And this was a bit frustrating, but after some brainstorming, we got to the conclusion that we should just create a training set where we combine different methods and adjust them such that they are physically correct. So we relied on the smooth potentials in conformational regions where the interatomic distances are not that large. And whenever we reached regions where it was incorrect, we switched to multi-reference method. And then we adjusted the potentials such that they matched the single reference methods. And in this way, we generated a training set. And we generated in total 17,000 data points. And I was very happy that I got help from 3 research internships during this time. And yes, we also needed to fit spin-orbit couplings, because the method that we used, ADC2, didn't have non-adiabatic couplings, so we used the approximation. But we had spin-orbit couplings, and we had about 800 spin-orbit couplings, which were all very similar. So it was extremely problematic to fit them. So what we did was we made use of the different bases that we had in quantum chemistry. So this is the direct output of quantum chemistry, the adiabatic basis, where states of same spin multiplicity do not cross, but states of different spin multiplicity do cross. So we have here smooth spin-orbit couplings. Now, if we use this Hamiltonian and diagonalize it, then we get spin-mixed states. And these states change based on the spin orbit couplings. So what we did was we predicted a Hamiltonian that was similar to the spin diabatic basis. Then we diagonalized it, and we also included information of the diagonal energies into the loss function. So we had more information, and this improved the training. And the diagonal energies were actually also very important for surface hopping to get these correctly. So with this, we had a final setup, and we did the dynamics. And here are the results. So after light excitation, the hydrogen atom dissociates as expected. But then it changes direction, and it just starts to move around the molecule. And I looked at the trajectories, and they looked actually quite good. So I couldn't say from the energies that it was wrong. And I showed this to my former supervisor, and he looked at me like I was crazy, and he told me that this is completely unphysical. But fortunately, we didn't throw it away, but we looked in literature. And he found a paper by Joe Bowman, published in Science, which talks about the roaming atom, which strays from the reaction path in formaldehyde decomposition. So this roaming dynamics were first discovered in highly excited formaldehyde, and we thought maybe we also discovered roaming in tyrosine. So we validated this reaction with multi-reference Caspidi-2, and we found that roaming was really the energetically favored path compared to direct dissociation. And this was really exciting for us because we wanted to know whether roaming led to the different reaction outcomes compared to the smaller chromophores or not. So we needed to analyze the trajectories. But now what we haven't considered is now we have millions of data points. Before, when we use quantum chemistry, we had a few data points, so we could just look at the dynamics. But now this was not possible anymore. And I also couldn't look at this because the computer crashed whenever I tried to look at more than 2 trajectories. And if you look at this, I plotted about 2 trajectories, and you cannot see anything. Maybe here's roaming, but okay. So we used unsupervised machine learning for this purpose to help us get more information. I guess that you're all familiar, but in case someone is not. So compared to supervised learning, where we know exactly what to learn, so we want to find a relation between an input and an output, like molecule and energy. In unsupervised learning, it's more like giving some data to the model, and we do not really know what to expect. So the model should learn something from it and give us some information. So that's the basic idea. And what we did was we took all the trajectories, we separated them into non-roaming and roaming trajectories, and then we used some unsupervised learning techniques to find some patterns in the data. And we used k-means clustering and principal component analysis. So what we found was that in non-roaming trajectories, we had 10% dissociation, 14% fragmentation, and in roaming, we had 50% dissociation and 1/4 fragmentation. So there is a big difference. And cluster analysis showed us some representatives that we found in both trajectories. So here, these 3 boxes show roaming and non-roaming. So we find, for instance, hydrogen dissociation as expected, p-methylphenol, which is also very pronounced in the mass spectrum, or other fragments. But what we only found in roaming trajectories were here smaller fragments, which are also visible in the mass spectrum. So when I first presented this at a conference, some colleague asked us if these roaming atoms were really the reason for this. So if they are radicals, if they're radicals or protons, but I will come to this later. So we also wanted to then investigate the kinetics, basically. And this was done experimentally by Stavros and coworkers. And they did time-resolved bump probe spectroscopy and velocity map imaging. And they found 2 reaction channels. So you can see here that we have a slow and a fast component. And within 1 picosecond timescale, the reactions are basically done. And what they also found that I already mentioned is that there was a size dependence in the dynamics, which means tyrosine is faster than the smaller chromophores. But in tyrosine, they found a very low signal-to-noise ratio, so they couldn't extract any useful information for the kinetics. So we used the photodynamic simulations to get some kinetic constants. And you can see here that they match the experiment quite well. So this confirmed that what we did was really somehow reasonable and that the dynamics were correct. And we found that the fast channel was due to dissociation in ground state and the slow channel due to dissociation in the excited state. Now, yes, so we have dissociation in ground and excited state. And if we now want to analyze these roaming atoms, whether they are radicals or protons, then we need to do charge analysis to find out whether it's +1 or 0, but for ground state and for excited states. And the problem here is that even though the charges are one of the most intuitive chemical things, it is very difficult to really get them because the results are not directly available by solving the Schrödinger equation. So we need to do some subsequent analysis, and this strongly depends on the partitioning scheme. So what we wanted to, how to overcome this problem was with a machine learning model that trains dipole moments. And this is the charge model that we adapted for excited states. This was developed by Michael Gastecker, Jörg Pehler, and Philipp Marquardt for ground state. And we adapted this for excited states. So what we basically do is we learn a dipole moment, but we learn this dipole moment by predicting atomic partial charges. And we know that when we sum the product of these atomic partial charges multiplied with the vector of an atom to a center of mass, that we get the dipole moment. So we predicted these charges, but we learned the dipole moments. And in this way, we had access to atomic partial charges for the ground state and the excited states, which would otherwise not be possible. And with this analysis, we then found that the roaming atoms were really radicals, which could probably be the reason for the smaller fragments. So to summarize this part, I hope that I could show you that machine learning can be used for photodynamics to enable longer timescales, and with combining different methods, we can describe more complex systems. And it can also help us to interpret and analyze results. Now, I have shown you two examples, a small model system and tyrosine, but that's basically how far we can get. So there are a lot of challenges that we need to address if we want to describe larger systems. One problem would be, for instance, where do we get the reference data from? It is extremely tedious to get to combine different methods as we did it. So this would be one of the challenges, to find a good method to get reference data for larger systems. And then it's also very important to study the influence of an environment or on protein environment. So is roaming really, does it also exist in solution or in a more realistic environment? And one of the other problems is, how do we enable a transferable description for excited states? So force fields for ground state exist, but for excited states, they are really challenging. And we don't really know whether singlet, triplet states, etc., are really transferable. And what about the couplings, the nonadiabatic couplings, spin-orbit couplings? How can we address this? And during my postdoc, we tried to find machine learning for excited states that are transferable. And I want to briefly also show you what we did here. So the goal of my current supervisor was to do machine learning wave functions for excited states for multiple systems. And this was really challenging because we didn't even know whether we can have transferable excited states. So we started with this. And our problem that we looked at was, if we want to design a new optoelectronic material, then we need to screen many, many molecules. And we want to find the best one. And traditional design approaches usually start with a molecule where we know that is relevant, like fluorine, for instance. Then we can change this molecule. For instance, here we can add one carbon atom, and then we study the optoelectronics. And even though it's very similar, the optoelectronic properties differ quite dramatically. But depending on whom you ask, you might end up with about 10 to the power of 20 to 10 to the power of 60 functional organic molecules that could be relevant in this research field. And we cannot just look at them individually and check their optoelectronic properties. Otherwise, we would maybe end up searching for a needle in a haystack. So we wanted to develop a machine learning model that can be used for high throughput screening. And the data set that we use for this purpose is the OE62 data set. And this is a very powerful data set because it contains 62,000 data points of organic molecules that were extracted from organic crystals. So they could be really potentially relevant in optoelectronics. And they contained PV0 orbital energies. And as Lucas has already mentioned yesterday, many people use orbital energies to approximate excited states. I'm not saying that it's accurate, but we also did it here. So you can see here in the OE62 data set how the molecules are distributed. So we have really very diverse molecules with very small atoms and very large atoms. And the chemical diversity is also quite high. So we wanted to fit the orbital energies. And I wanted to use the approach that I developed during my PhD. So we wanted to use SNET as a descriptor and a multi-state neural network for the orbital energies. And we wanted to train the orbital energies of the molecules in the OE62 dataset. Now, when I started this and approached Reinhard Maurer, then he told me that this will never work because he already kind of tried it. And I didn't believe him, of course. So I tried it, and it didn't work. And the reason was, as for normally excited states, that we have here cusps in the orbital energies. But it seemed to be more dramatic the more states we had and the more molecules we had. So we had to now search for a solution for this problem. And what we did was we adapted the SNET model and named it SNET plus H, where H stands for latent Hamiltonian. So we adapted the last layer of the network such that it matched the latent Hamiltonian. And this latent Hamiltonian could be seen as a machine learning basis for orbital energies. So it is symmetric, but not really physical. But if we diagonalize it, we have eigenvalues, and the eigenvalues we can match to the orbital energies. And in this way, we outsource the problem of non-smoothness of the eigenvalues to get something that is smooth. So this approach then finally worked, and we wanted to use it. We wanted to use it for predicting photoemission spectra. So the fitting worked. But then we compared to experiment, and you can see that they do not really match. And as expected, DFT orbital energies are not good approximations. So we required higher accuracy. And it is very difficult to get higher accurate excitation energies for large systems and many molecules. But this data set also contained 5,000 data points at a GW level of theory. And I guess you've already heard in one of the previous talks that with GW, we can correct DFT orbital energies that are wrong due to the neglect of the self-interaction energy. And G0 W0 is the most simplest approximation. It's a single-shot perturbation. And the perturbation is the electron that is added or ejected. So what we get are quasi-particle energies that are really accurate and can be used to get photoemission spectra. But GW is way too expensive to compute many data points, and we only had 5,000 data points. So we needed to learn from little data. And what we used in order to get there is the delta machine learning approach. So those who are not familiar with this, we usually machine learning, we always look at learning curves. And we know that if we plot the number of data points against the prediction accuracy in a logarithmic scale, then it should be linear. And if we have a conventional machine learning model, like 62,000 data points, we get to that desired accuracy. But now if we have 5,000 data points, the accuracy drops. And this is problematic because we want to have accurate GW values. So we don't have enough data. And if we can overcome this problem by learning the difference between GW and DFT. Because what was found in previous studies is that learning the difference between two methods is much easier and much smoother than learning a method itself. So with this approach, you get away with much less data, but get very accurate results. So we trained one machine learning model on the orbital energies of DFT, and then we trained a second on the difference between the first model and GW, so that we can use both models to get quasi-particle energies. And this model we then validated, and it looked quite good compared to experiment. And we wanted to apply it now for high throughput screening. So we were very happy that we had our model, but then we searched for data, and we didn't know where to get the data that we could screen. We could screen the OE62 data set, but that's it basically. So we then started to use generative machine learning models for molecular design. And we used GSNet, which was developed in Klaus-Robert Müller's group by Niklas Gebauer. And this model is an autoregressive generative neural network model. And it's unsupervised learning. And we try to model a data distribution And we want to predict the data distribution that is similar to the original one. So the loss function is basically the similarity between the molecules that are trained and that are predicted. And this model is very powerful to create molecules in 3 dimensions and structures that are close to the equilibrium. So a very talented undergraduate student worked with me on this during the summer, and he adapted GSNet such that it works for the OE62 data set. And with this, we could then predict arbitrarily new molecules and could screen them with the other model. So I often replace the generative model with a magic hat, because in principle, we can get any number of molecules we like. And we then screened this with our machine learning approach for quasi-particle energies. And then we had selected molecules with target properties. And in principle, this would already be very good to find some new molecules with special properties, but we wanted to get a step further. So we wanted to know whether we can create molecules that have properties outside of the original data set. And Niklas Gebauer has already shown that GSNet can be biased towards a certain chemical region. And we wanted to bias GSNet iteratively towards molecules with targeted properties. And the target that we aimed for was small fundamental gaps. So this is here the distribution of the fundamental gaps in the OE62 dataset. We then used only these data points with the shaded area, and we biased the generative model. So we got a distribution that had fundamental gaps that were smaller. We again biased the model against these values. And we did this iteratively until we had a distribution that was outside of the original dataset. So we predicted these values with a machine learning model that we developed before. And we were quite critical, and we didn't know, okay, is this maybe outside the training regime and completely nonsense, or whether it makes sense. So we selected random molecules from these 3 iterations, and we computed GW values and also compared to the machine learning prediction. And you can see that in yellow, all values are smaller than those in the OE62 dataset. And our machine learning model was still quite accurate. And Joe Gilkes, a PhD of Reinhard Maurer, then looked into the chemical space with me, and we did principal component analysis. And you can see here the gray data are those molecules that are in the OE62 dataset. So this is the chemical space spanned by these molecules. And with progressive iterations, we kind of move into a certain region of chemical space. So we do not leave the chemical space, but we leave the property space. And that's why also the machine learning model for the energies is quite accurate. So yes, and with this, I come to a conclusion. I hope that I could show you that machine learning is also very powerful for chemistry and application and for excited states. And yes, the main challenges are how can we make all of these things transferable and use it also for dynamics? And what methods can we actually use to get excited states of more complex systems, materials, hybrid interfaces? And one way maybe would be delta machine learning. But yes. I also want to thank my current research group and some amazing collaborators, funding agencies, and I want to thank you for your attention.